So, let us see the approximations which are made to reduce the number of species. Okay. So, if you have a multi-component mixture and so n species constituting that mixture, then we need to solve n minus 1 governing equations. So, n minus 1 governing equations have to be solved. So, these governing equations are partial differential equations which involve nonlinear source term. So, the rate of production or consumption of each species kilogram per meter cube second. We have seen already that the exponential dependence of the rate coefficient. So, for each species you have to calculate. So, for example, you can see this. This is the way you calculate the net rate of production or consumption of a particular species involving several reactions. So, this is a nonlinear term because of all these rate coefficients are nonlinear function of temperature. So, involving this equation you get a nonlinear source term. So, solving this n minus 1 governing equations are very actually tedious and computation efforts are required, more computation efforts are required. So, it is better to always reduce the number of species especially when the problem which you are trying to solve is a bigger in scale. Okay. So, two approaches are used to eliminate the number of species. So, when we say eliminate, we do not eliminate the species itself, we eliminate solving the governing equations. Okay. So, how to do that? There are two approaches. The first one is called steady state approximation. Steady state approximation is the first one. Second one is called partial equilibrium treatment. So, these are the two approaches which are commonly used to eliminate the solution of the solving governing equations. So, these species are calculated as function of other species and say reaction coefficients, rate coefficients and partial. See, when you implement this partial equilibrium, you involve the Kp value and so on. Okay. So, the first one basically steady state approximation involves with radicals, eliminating radicals which are highly reactive chemical species. And what happens is when the chemical reaction starts, radicals are formed in high quantities because of the chain propagation and chain branching reactions. So, chain propagation reaction produces at least one radical and chain branching reactions produce multiple radicals. So, high quantities of radicals are produced because initially the concentration of reactants are very high. So, based upon the initial concentration of the reactants, high quantities of radicals are produced. Okay, radicals are highly reactive. So, what happens is initially the concentration build up will occur. So, due to massive production, the build up of concentration will occur. Once the concentration reaches a higher value, the reactions involving its consumption will have a higher rate, obviously because the rate of reaction is dependent on the concentration of the reactants also. So, initial build-up of the concentration of the radicals will lead to higher reaction rates for the reactions involving these radicals. So, the radicals are also rapidly consumed now because of the higher reaction rate of the reactions involving these radicals which consume them. Okay. Now, so basically this can be chain termination reactions also which can produce the major products. Okay. Now, once this is consumed, it is also simultaneously produced because of the other the reactants are being there and they are also producing radicals through propagation and branching reactions and they are consumed to termination reactions and so on. So, they simultaneously occur, production and consumption. However, the reactions forming the radicals are at a lower phase or slightly slower than the reactions consuming this. So, now the production of the radicals becomes slower and the consumption becomes higher. Okay. So, this happens to several radicals. Okay. So, that is the main thing we have to physically understand and select these radicals and put them in what is called steady state approximation. Okay. Now, since the reaction forming the radical being slightly slower than the reaction destroying the radical, at one stage rate of formation of these radicals will be almost the same as the rate of its consumption. Okay. So, they form and they just destroy it, that is all. So, that means that they do not have any time dependency, at any time they will produce and they will be destroyed, that is all. So, and also what happens is then the chain reaction continues. At one point you will see that the concentration of the radical becomes very small, because they are produced and they are consumed at a very small faster rate. So, the concentrations are because the radicals become very small when compared to the major species, okay, other reactant product species. So, under such condition these radicals are handled with steady state approximation. So, we will consider example to illustrate how it is. So, let us consider a set of reaction like this: O plus N2 giving NO plus N and N plus O2 giving NO plus O. So, here you can see that the nitric oxide formation is called Zoltovich mechanism, two important reactions producing nitric oxide. O plus N2 at the rate of the rate coefficient for that reaction is K1 producing NO, and N plus O2 the rate coefficient is K2 here. The first reaction forming N is slow than the second reaction, which is forming the N plus O2 giving NO plus O, that is faster. Okay, so, the N is consumed at a slightly faster rate than it is produced in the first reaction. That is what the important note you have to make. So, the first reaction forming N is slower than the second reaction consuming N. So, what happens is at a particular time the concentration of N decreases to a low value. So, the rate of the concentration of N with time is nothing but the first reaction it is formed. So, plus K1 concentration of O, concentration of N2, minus in the second reaction it is consumed. So, minus sign, minus K2 times concentration of N and concentration of O2. So, after the initial transient period, initially this will be not 0 transient period. So, there will be some build up and consumption, etc. Now, after the transient period is over, the N is produced and it is consumed faster. So, now what happens is the value of N will be low, and also the rate of change of concentration of N with time approaches 0, a value of 0. So, it tends to 0. So, we can say you can put left hand side 0 here. So, 0 equal to the forward reaction rate of the first reaction and minus the reaction which is forming NO. Okay, now, from this we can write the concentration of N in terms of other species like this. Okay. So, here N I put a subscript steady state. So, SS is calculated as K1 into concentration of O into concentration of N2 divided by K2 into concentration of O2. So, now N is concentration of N is calculated and it is used in the calculation of properties and other diffusion coefficients, etc. However, a species conservation equation need not be solved for N, because the concentration of N is calculated using concentration of other species like O, N2 and O2 and the K1 and K2, which are the rate coefficients of the first and second reactions what we saw. So, in this way this species is like now eliminated from solve, but this species still is in the mechanism, but we need not solve a separate governing equation for this. So, we can just calculate once O, N2 and O2 are calculated, I can calculate the concentration of N and use it for other purposes. Say for example, calculation of Cp of the mixture, diffusion coefficient of the particular species into mixture, etc. For all other activities, you will see that the concentration of N will be used, but a separate equation for N cannot be, is not needed. So, that is the advantage of doing this. So, in a steady state approximation which can be applied to radicals and fast reaction species which are produced initially at a higher rate, but also consumed at a much higher rate in the subsequent proceeding of the reaction, can be calculated using a steady state approximation. Okay. So, that is what is illustrated here. So, this is one of the approximation or methods which will be used to eliminate the species. The second treatment, second way to eliminate a species like solving the conservation equation of the species is partial equilibrium treatment. Okay. Now, the mechanism, chemical mechanism has several reactions. Out of them, say, some are very fast, some are very slow, and so on. So, like very extremely fast reactions are chain propagating reactions, chain branching reactions, etc. Slow reactions, etc. are say termomolecular, 3 molecules combination reactions, etc. are slow reactions. Normally, no, these slow reactions only will control the overall rate of the mechanism. See, for example, in a road, if there is a slow moving vehicle, that will actually decide the speed of the other vehicles following it and so on. So, similar to that, the slow reactions are the rate determining reactions. So, by the time the slow reactions are going to be completed, the fast reactions would have been completed much faster and they would have reached the equilibrium condition. So, at a given temperature and pressure, they would have completed and they would have reached the equilibrium. The slow reactions are still going on. So, fast reactions can be considered to be in equilibrium. So, this selective, I am not considering everything in equilibrium. So, I am not giving so much time to all the reactions to complete and all the products to complete equilibrium. We are not doing that. What we are trying to do is only the selective, this selective treatment of assuming equilibrium for certain reactions are done. So, this approach is called partial equilibrium treatment or a partial equilibrium approximation. We will give an example again to say what we are trying to demonstrate here. So, consider the fastest reaction O2 giving 2O, it is a very fast reaction. So, here the forward rate O2 producing 2 O atoms or the reverse rate 2 O atoms combining to form O2 are very fast. So, that this completes within a very quick time, okay. And what happens after completion, this becomes an equilibrium. So, based on the temperature and pressure, certain amount of O2, certain amount of O will be there in the particular mixture. So, the equilibrium can be assumed for this reaction and other reactions still are going on. So, when you do this equilibrium for this, I can eliminate O, for example, okay. So, what I would do here is I will consider the reaction O2 giving 2O, that is the fastest reaction, that should be to be in equilibrium, and I calculate the equilibrium constant based upon partial pressure. So, that is Kp. So, what is that? Kp will be equal to P, the product, P partial pressure of O to the power of 2 stoichiometric coefficient divided by P naught square divided by the reactant is partial pressure of O2 by P naught. So, that when you write that, you will get partial pressure of O square divided by partial pressure of O2 into P naught, that is atmospheric pressure, the standard pressure. So, now in terms of concentration, you can write it as concentration of O square RUT divided by concentration of O2 into P naught. So, now I can calculate the concentration of O in terms of concentration of O2, partial pressure based equilibrium constant and the atmospheric pressure RU and T, etc. At a particular temperature, I can calculate the concentration of O with this. That means I need not solve a partial differential equation to calculate transportation of the O. So, O can be calculated by this equation. So, O is now eliminated from the partial differential equations. So, concentration of O is written in terms of concentration of O2 and Kp at a given temperature. So, this way these two approaches, we have seen that the first approach, steady state approximation, can be used to write the concentration of radicals, some radicals as a function of other species, rate coefficients, etc. So, that a partial differential equation need not be solved for that radical. We can assume several radicals like that. Similarly, this is one of the reactions which we consider to be in partial equilibrium. We can also consider other reactions which are much faster, and then those reactions can be assumed to be in partial equilibrium. So, that the species radicals, again some radicals like that, can be assumed to be in partial equilibrium, so that they can be calculated, the concentration of them can be calculated using the concentration of other species, temperature and so on, and Kp basically. So, these two approaches, like steady state approximation or the partial equilibrium approach, are used to eliminate solving the partial differential equation or the conservation equation for several species. So that even though these species are going to be used for calculating the Cp values, other properties, other diffusion coefficients, etc., mixture enthalpy, mixture properties, etc. So this, there is no need to solve a separate conservation equation for that, because the concentration of these species can be solved using the concentration of other species and the reaction rate coefficients, partial pressure based equilibrium constants, and so on. So these two approaches help us in eliminating solution of partial differential equations. So if there are n equations, if we do not apply any of these rules, then approximations, we will end solving n minus 1 partial differential equations. So if n becomes very high, then we will be solving too much of equations. So when you try to put some conditions for this and eliminate say 10 equations, so we need to only solve n minus 11 equations in that way. So that is the advantage of this. Okay, now so far we have seen the rate coefficients for elementary reactions, correct, and the way, for example, here we have seen in a mechanism several reactions are there. From that a particular net rate of consumption or production of a particular reaction species like O2, how we have to write, we have seen, and all these equations R1, R2, R4, etc. are elementary reactions. So elementary reaction rates involve the concentration of the reactants raised to the stoichiometric coefficients. Here for example, HO2 and H react to form O2 and H2. So here this HO2 to the power of the HO2 concentration is 1. That is stoichiometric coefficient of this particular reaction itself. Okay. So we have seen how to do that for elementary reactions. Now we will see how the global reaction rate is calculated. Okay. Now for elementary reactions, what we are told is there is a kinetic theory basis for arriving at the way the reaction rate is written, like the Arrhenius form, A pre-exponential factor into exponent of minus A by RUT. Okay. Or if you want to add a third temperature factor, T power m also is multiplied there. Okay. But for a global reaction, there is no basis, because these are molar based reactions. So only by careful experiments we will attain the reaction rate. Okay, we will be able to get the reaction rate for this. Okay. So normally when for what this particular global reaction rate is useful, for doing bigger problems, okay, where the dimensions of the chambers are higher, it may be two dimensional, 3-dimensional simulations and so on. In that case, no, using a detailed mechanism will be very tough. So that in several cases we can use a global single step mechanism like this. And basically this is for each of this we have to determine the rate coefficient. For example, if you want to do ignition delay calculation or flame extinction characteristic of a particular burner, etc., then a single step reaction involving that can be tested, and the rate coefficient can be determined, and that can be used for doing parametric studies. Okay. So let us consider the reaction of methane and air. Okay. For this reaction, the rate of change of concentration of methane is given by again the same type of Arrhenius rate coefficient, pre-exponential factor and activation energy. So A times exponent of minus EA by RUT. Okay, this is the Kg I say. So global rate coefficient, Kg is a strong function of temperature as you see here. If you want, you can also add T power m, that is also possible. Okay, here you can also add this, multiply this to this. Then concentration of methane to the power m and concentration of oxygen to the power n. Okay, now this m is not 1 or n is not 2 into 4.76. It is not stoichiometric coefficients. M and n are determined by the curve fit, in which you conduct experiment in several isothermal conditions and measure the concentration of CH4 as a function of time, and then fit this curve to get this values of m, n, A, E, A, etc. So the values of A, E, A, m and n are obtained from careful experimental data. So, m and n are not stoichiometric coefficients and they need not be integers also. See, for example, m can be 0.25 and n can be 1.5. So, that the total order of the reaction can be m plus n, which is equal to 1.75. Okay. So, similar values we will get. So, there is no need that we have to fit only integers here. Okay. It can be the 0.25, 1.5 etc. also. So, the overall order of the global reaction. So, this is where we are now defining the order of the reaction. Okay, order of the reaction for elementary reaction is same as the molecularity. So, number of molecules participation, but here there is no molecule business here. So, there is no molecular definition here for the global reaction. However, you can see that the order can be defined from the rate equation. What is the order? The powers of the reactants, the concentration of reactants which are rates to, those powers when they are added up, that will give the order. So, in this case m plus n will be the overall order of the reaction, and for hydrocarbon fuels the m plus n lies in between 1.7 to 2.2. So, again indicating that the order is second order reactions. Okay. So, global reaction rate is obtained only from experimental data and it is actually done for several purposes. It is not, we cannot use it for, see, if you have a elementary reaction based mechanism, detailed mechanism with several steps that can be used to obtain anything, say for example ignition delay, flame extinction, accurate temperature, etc. So, structure of the flame. So, we will see later. So, that elementary based reaction schemes which are several reactions and several species are involved in that can be used for getting all type of oxidation features of any particular fuel. Okay. However, when you try to construct a single step reaction like this, we have to get the coefficient for a particular type of problem. For example, if ignition delay, the coefficient can be a different way of expression, the A and dA value can be different. If you want to predict flame extinction, the A and dA value can be different. Okay. So, even m and n values are also can be different. So, for a particular condition we try to do experiments and try to correlate, this is called correlation, experimental correlation. So, empirical correlations are got for the reaction rates. Overall, this is called overall reaction rate, the rate at which the main fuel species is consumed. So, you can see that this is the rate at which the oxygen also will be consumed and the rate at which CO2 is formed and so on. So, based upon here the mass basis also you can write. So, for example, if 1 kg of methane is consumed, so how much oxygen it takes, say S kgs of oxygen, then if 1 kg of methane is consumed, then S kg of oxygen will be consumed. Similarly, the products. So, if 1 plus S kg of total product should be formed, so that will be formed. Okay. So, so this is the way we write the overall reaction rate for a global reaction. Now, the global reaction need not be always single step. Say in a single step if you write, you have only major products CO2 and H2O only you have in this. But if you want to include say a few more, say CO, H2, etc., which will be more accurate. So, our calculation will be more accurate when you involve CO, H2, etc. in the reaction scheme. So, you can also have multiple steps for the global reaction. Okay, when I say multiple steps, what is the difference between a mechanism involving elementary reactions and a mechanism involving global reactions? Here you can see that the reaction in each step is only a global reaction. That means they cannot take place in one step and they are not molecular level reactions. They are again specified by the number of moles only. Okay. So, multiple step reactions are there. For example, two step reaction mechanism for methane, in which what we do is CH4, it will not burn with 2 times air, it will 2 times oxygen molecule, it will be 1.5 times oxygen. First step will produce only CO, but please see that all the H2O will be produced in the first step, all the H2O will be produced, but CO only will be produced. The second step, the CO will be oxidized with the remaining, see 2 times oxygen is required, here 1.5 times is used to produce CO, and remaining will be produced in the second step, and CO2 will be finally formed. So, again please understand, this is only one way reaction, these two are only one way reactions, and they are going to occur in several steps again. So, these are all global reactions. Okay. Again by experiments we can get the values of K1 and K2, this is the first reaction. So, say Kg1 and this is Kg2, this Kg1 is nothing but the rate coefficient for the reaction 1 which produces CO and H2O. Kg2 is the rate coefficient for the second reaction which consumes CO to produce CO2. Okay, so, global reactions, these two reactions are global reactions. Okay, now similarly researchers have come out with 4-step mechanism for any hydrocarbon, say maybe alkanes here CnH2n plus 2. Okay, the first step produces CO plus H2. So, now please see this, in the single step global reaction we do not have CO at all, we have only CO2 and H2O. In the 2-step H2O dissociation is not taken into account. So, H2 is not there, but CO is included, because CO's consumption is very important for several cases. So, this heat release due to CO oxidation is very important. So, that is taken care by this. But in several scenarios if H2 also is required, so then the 4-step mechanism is formulated, in which the first step will take some amount of O2. Okay. When I say O2, you can also write plus 3.76 N2 and write the N2 in the right hand side also. So, that is also, so it is not only oxygen base, it is also air base. So, wherever I put O2 in the reactant side, here you can also put O2 plus 3.76 N2. So, that the nitrogen treated as inert will come to the product side. So, here first step produces CO and H2, second step this H2O, see for example H2O will react with this to form CO and H2 again, but how H2 is formed? H2O is formed by reaction between H2 and O2, and this is formed. So, this will go to this now and react with this alkane to form CO, and further CO and H2 are formed. Then so coupled equations, they are coupled. Okay. Then finally we have already discussed this water gas shift reaction, CO plus H2O giving CO2 plus H2. So, it is called water gas shift reaction. Okay. So, like this, these are all global reactions, all are global reactions. See, you can wonder these two can be elementary reactions, okay, these two can be elementary reactions, but these two are global reactions in this. So, you can see basically the calculation of formation of CO, and here this plus H2O, alkane plus H2O giving CO plus H2 etc. should be carefully determined by experiments, and the dates are formulated. So, Kg1, here Kg2, this is Kg3 and this is Kg4. Okay. So, now this set of equations can be solved to get this detailed it is not as detailed as the elementary reactions will do, but this will give you additional species like CO and H2 to be participated in the reaction, so that you will get better prediction of temperatures and other features, extinction and ignition etc. Okay. So, this is about the global reaction rate.